Okay, so we have a good bit going on in this class. It's worth talking about that. So there's an exam that will take place a week from tomorrow. That means that I'm getting a study guide to you by tomorrow. And that's going to be, I'll tell you what the study guide looks like. It's just a list of topics that we have covered, but it's not the broad topics. It's more specific topics. And some of those topics are phrased in the form of questions. How do you handle this? So the way that I recommend using study guides in my classes is just to go through that document, and that document can become your study sheet that you get to bring with you to the exam. Just kind of go topic by topic and fill in that information with whatever we have covered. Example problems, if you would like, you can print the slides or portions of the slides. I don't care if that's on your note sheet. It doesn't have to be handwritten. You can print, use, I really don't care what's on it, whatever you want. I designed these exams to be problem solving heavy and implementation heavy. So the recommendation is that you spend the time on the prerequisite knowledge and content and getting practice so that you're ready to come in and perform in that 1 hour. A lot of my exams can run up against that hour, especially if you spend some of your exam time working on understanding material or trying to recall material. So the more of that you can do and have on your note sheet, the more likely you are to be able to spend that hour productively solving the problems that are on the exam. Next Thursday will be a review period. So a week from today, I will have no new content, nothing prepared except for answering your questions and going over practice problems that are things that you have questions about or would like additional practice with. So it's best practice, I find, if people come prepared with 3 to 5 questions, or there are 3 to 5 topics that they feel like are weakest, and then say, I would like to work on this idea. If that requires any preparation on my part, like to know exactly what problem to throw on the board that will go over some particular topic, please email me at least 24 hours in advance so that I can prepare that material for you on that day. I can come prepared, so I'm not digging around trying to find a practice problem while other people have questions. I would like to utilize the full period if there are questions and examples that I can use to fill that period. Next, the TA has agreed to what I like to do, which is allow people to turn in assignments early and make sure that you get feedback on assignments before an exam. So the earlier you submit your assignment, the more likely you are to have feedback for it by the time that the exam rolls around. If you submit by Monday, I can guarantee that you have feedback. So the TA has said, if everyone submitted on Monday, I could turn everything around by midday Thursday. So you have time to look at it, study it, prepare for Friday's exam. If you submit later than that, he'll just get added to the queue of what the TA goes through, and he'll get through as much as he can in the time that he has for that ahead of the exam.
So our lecture is going to be, our exam is going to be up to date on homework completion or lecture?
Mostly homework completion. So yeah, the topics that are on the study guide will tell you everything that could reasonably appear on the exam, but what I try to do to the best of my ability, unless it's going to really screw with the rest of the course in some meaningful capacity, like there's just 40% of the course material that is now pushed to one exam because of homework. I try to keep the long-term health of the class in mind, but yeah, they're designed to be what you have turned in for homework. So the lecture material will probably be well ahead of that material. I think the cutoff for what is on this first exam is probably what we are covering today. Or pretty close to what we're covering today. Let's see, I think that's everything that we need. Any questions about the upcoming schedule, what we're currently covering, what we're doing for the next week? Okay, we will dive into this. At the end of last class, we were covering reducing this DFA down to its minimal form. We went through that process. What would be most useful to people here? Do we want to reproduce that process in a bit slower and more useful detail, or do we just want to summarize it and get to the next thing? How are we feeling about distinguishability, indistinguishability, the ability to map states onto each other based on that idea?
I'd be okay with a quick summary.
Quick summary and review.
Kind of help you out.
Yeah.
It works.
Yeah, so remember, we're working on a half diagonal triangle table, whatever it is that we want to call it, where we don't care about the order of the nodes. We only care about pairing the pairs of nodes. So that's what leads to that half full table. If we cared about the order, then we would care about the full table. So in this particular example, I like to draw them either on a row or a column, just write down every single node name, Q0, Q1, Q2, Q3, and Q4. That was everything, yes. And then you do everything except the first one on the other. So I think I did it the other way this last time. So now we have Q1, Q2, because Q0 doesn't need to be compared to Q0. Q0 is compared to everything here, so there's no reason to compare it to anything else. Q3, Q4, and we just have our half table. We need to compare Q0 to everything, so these become our question marks. We need to compare Q1 to everything past itself, Q2 to everything past itself, and Q3 to everything past itself. So that's where we start. The rest of this is irrelevant, and we can just kind of draw. None of that matters. So we start by marking everything as distinguishable that has every pair that is different finality. So we'll go through and say Q0, Q1, same finality. Q0, Q2, different finality. They're distinguishable. Q0, Q3, same finality. Q0, Q4, different finality. We'll mark them as distinguishable. Q2, Q1, is that right? Yes. Q1, Q2, different finality, distinguishable. Q1, Q3, same. Q1, Q4, distinct, distinguishable. Q2, Q3, distinguishable. And Q2, Q4, same. Q3, Q4, distinguishable. All right, so that's kind of the initial pass through thinking about that. So with a string of length 0, we can find the distinguishability. So note that the first pass through this is looking at strings of length 1. The next pass is looking at strings of length 2, length 3, length 4. But we're doing it by only looking one character ahead at a time and back propagating that distinguishability until we make no changes. So we loop around, we have 4 question marks. We're going to ask for each pair of these states. We're going to see if we can find, with a single input character, can we make a transition that goes to distinguishable states? So from Q0, Q1, we said on a 0, where do we end up? Q0 goes to Q1, Q1 goes to Q2. So the initial state pair Q0, Q1 ends on a 0 on the state pair Q1, Q2. If we look into our table at Q1, Q2, we see that they are distinguishable. So on the string 0, if you're in these two states, you end up in states that are distinguishable. So because of that, where we started is distinguishable. There is a string from these two states that one state would move to accept and one state would move to reject. Because of that, that is the definition of distinguishable. So these are distinguishable. This question mark, Q0, Q3. On a 0, they end up both in Q2. On a 1, they end up both in Q4. So no evidence at the moment that they are distinguishable. We'll move on. Q1, Q3. I already did that. Q0, Q3. That's different than Q1, Q3. Q0, Q3. On a 0, we go to Q1 and Q2, which we just asked about. So that's distinguishable. This question mark, Q2, Q4. On a 0, we end up in Q1, Q4. If we look at Q1, Q4, we see distinguishable. Exciting. Means this is also distinguishable. Since we made at least one change to this table, we are going to loop around and do it again for every remaining question mark. We go back to Q1, Q3, and we see that on a 0, we meet at Q2. On a 1, we meet at Q4. No change. Since we looked at every single question mark in this table and made no change, every remaining question mark is marked as indistinguishable. Once this process completes, we care about looking at the pairs of states that are indistinguishable, and we can get rid of one of them. And it does not matter which one you get rid of. We just have to identify transitions into and out of that state. So last time we got rid of Q3, let's get rid of Q1 this time. So you would say this transition into can go away, but we need to reroute it into that same transition into this other state. So that would say that Q0 on a 0 goes into the equivalent indistinguishable state. This transition out should have a transition out to the same state. If it doesn't, you would create a transition out to the state that this goes with a transition out to. But it's a DFA, so it should already have it. So that just allows us to get rid of this transition. If we take the 0, a 0, 0 gets us to this state, and before a 0, 0 also got us to this state. This transition into Q1 from here, if we remove this edge, we no longer have the ability for Q2 to read a 0. Where should it go? Into Q3, yeah. So we're going to reroute this edge to there. This edge as a 1 going here is the same as a 1, since these two states are indistinguishable, so we can just get rid of this edge and no further work is required. So now that we've removed every edge into and out of Q1, we can remove the vertex. It's no longer part of this direct graph. And now we have the equivalent DFA to this DFA, but now with one fewer state. And you would loop and do that process for every pair of indistinguishable states in this table. Question?
So, kind of a compilers do optimization.
In some senses, there are lots of different subcomponents to compiler optimization, but yeah, a lot of the times they're very similar styles to this kind of analysis, at least. Which is why we cover, I just love optimization algorithms. So I put them in as many classes as I teach as I can, because it's one thing to do something well, and it's another thing to do it optimally. You can solve the problem, but if you can solve the problem in as fast as possible form, you have an advantage. And if you're in any kind of competitive environment, be that a game, be that cybersecurity, be that research, be that if you're working at a company and you optimize the result, your program will be faster than the competition who can't think that way, which will give you, your company, a competitive edge, reason to promote you, so that you design the future optimal solutions rather than just have to implement them that someone else tells you to do. So that separates a code monkey from a leader. If you want to go into the industry and be a code monkey, know how to do something in general. You want to be a leader, know how to do it optimally, or how to think about the problem, break it down, and find a way to do it better. That's what gets you promotions. Any other questions? I'm erasing before I ask, which is probably not good.
All good.
All right, I think if the process is clear, we can move forward. You can always look back at this recording. Those will exist. So I have the whole process listed on the next slide. I don't like to go through the process without the image there, rather just go through it while you can visualize it. But here is the words for at least splitting them up in also in terms of the equivalence classes, that way of thinking about it so that you can do that. But yeah, we've basically already talked about the entirety of the remainder of these slides because pictures are better than words. So yeah, generate equivalence classes for each set of the states, create a state labeled as the concatenation of the old states, associated transitions into and out of the newly merged states and merge them. Exactly as we just showed. So there's the solution. We found that we were able to combine 1 and 3 together. And it creates a new DFA that doesn't quite look exactly like what I just showed, but that's only because of the vertex placement. The actual vertices and edges are the same. Last minute questions on this process before we move on to the next idea. Being in this class is just content after content after content, idea after idea, just rapid fire, because there's so much to cover. But I assume that as you start to get practice on homework, questions will arise. That is what office hours are for. And I hope to see a good chunk of you as you have those issues. Do not struggle without asking for help. All right, next concept. Regular expressions. Because we have seen these before in terms of the programmatic regular expressions, we're going to talk about theoretical regular expressions. They're actually the same idea and map directly onto each other, but how you utilize regular expressions will have a few frills to them and syntactical minimizations to them, but they represent the same idea. So I think we talked about this a few class periods ago, but familiarity with regular expressions or use them in some capacity or another. Yeah, so they represent the same class of language that we've been talking about. Any kind of language that we can draw a DFA for or draw an NFA for, or write what we're going to talk about next, a regular grammar for, you can also create a regular expression for. It's the same class of language that allows you to search through and parse text, that allows you to, in games, identify any collection that can be defined without memory storage. So are there other ways to describe regular languages other than with both of these DFAs and NFAs are both finite state machines because they have finite memory? The memory does not scale, it is bounded by the size of the DFA or NFA. So regular expressions, another way to do that, which is cool. They look very much like math expressions. They consist of some of the concepts that we have discussed so far in terms of set notation. So they represent and contain strings and symbols made up from the alphabet and parentheses that can override a default order of operations that we will talk about. They involve set operators rather than mathematical operators, but sometimes they will look like math operators, but they have a set needed. So the plus denotes the set operation union. A dot and or concatenation will represent the same thing, concatenation, rather than multiplying together. What would be multiplication in a math expression is just concatenation. Superscript star, star closure, 0 or more repetitions, same idea. And an unnecessary last component to this that you don't ever need, but saves you a little bit of space, is a superscript plus that just gives the positive closure, 1 or more repetitions. You can always just say, to do 1 or more, you say the thing, and then the star closure. 1 for sure, followed by 0 or more, it would be exactly the same thing that followed it. But since that is just repetition, it's better to just condense that, use the plus, and that way your regular expression is shorter. So plus is perfectly okay in the class, but you do not need plus to define the set of possible operations for regular expressions. So yeah, very frequently used outside of computer science theory. Any complex search in a text editor or browser, if you wanted to identify things like, I want to find all phone numbers in this document, to say digit, 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 dash, digit, 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 without an area code. Or you could say open parentheses, digit, 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 close parentheses. And that would be the area code. You could identify every area code within a document. You could identify every year as 4 consecutive digits with spaces on either side. You could identify social security numbers in a document very quickly with a regular expression. They're more popular or becoming more popular in other things that computer scientists don't necessarily, or data scientists don't necessarily deal with. Like, for instance, item-driven games can allow for regular expression search within them. I play Path of Exile. I utilize regular expressions all of the time to identify items that have particular affixes and values of those affixes or certain socket color combinations within my stash. So the same idea can be used to do that. If you're looking at a vendor window and you're curious, does the vendor sell an item that has this particular combination of mods or one of this associated combination of mods for me to make a further decision on whether I want to purchase it? You can throw that regular expression in a search, if the game allows you, in the vendor window, and it'll highlight all of the items that are interested to you, so you don't have to go through every single one and look at it. So plenty of uses out there. As the game design professor, whenever I see this out in games, I go, whoa, connection. This is cool. So yeah, Path of Exile is the one that I'm familiar with, but it's becoming more popular in other games as well. So let's give you a theoretical simple example of a regular expression. So language, alphabet is just ABC. A regular expression could look something like this. This reads A union BC, that entire thing, 0 or more times. So you could read this as the star closure of A union BC. Let's take a second and think if, can we identify and describe what this represents? If we were to write a set of strings that are contained within this language. First of all, how could we do this in some kind of logical or intuitive order?
We can find out what the two separate, the sets of the two separate halves are, so when they're union together, that's the whole language.
Okay, yeah, so star closure says there's some amount of repetition. I like to think of this is an element and this is an element because they have to appear together. This BC has to appear next to each other to be one of those elements. So what are all strings in this language that have length 0 according to the length number is going to be some number of these elements. So how many strings are there of length 0? 1. Since it's the star closure, it can be 0 or more. So this will accept the empty string. So we're going to throw that in as the first string in this language. How many strings are there of length 1 according to either the left-hand side or the right-hand side of this union?
2, right?
2. Yeah, we're going to have A, and we're going to have BC. For all intents and purposes, BC is a single character because it has to come together. It is 2 characters, but it represents the right-hand side of this union. And we'll see that when we start to think about this in terms of combinatorics, it's way easier to think about this in terms of this is one element rather than this is 2 characters concatenated together. How many are there of length 2? 4. That's right, because of combinatorics. And it's easier to see if you think about it in that regard. So what are they?
A, B, C, B, C, A.
Yeah, so basically you can think of this kind of like coin flips or anything else that's binary. We can get left, left. We can get left, right. We can get right, left. I don't know how I want to represent that, but right, left, and right, right. So if we do left, left, that's AA. If we do left, right, that's ABC. If we do right, left, that's BCA. And if we do right, left, or sorry, right, right, that's BC. BC. How many are there of length 3?
8.
8, 2 to the third. Left, 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 right. It's the exact same combinatorics if you've seen it in a stats class of anything binary, flipping a coin, true, false, truth tables from discrete, anything like that. So if you think of it like that, you can use combinatorics as a way to start to write out this. And eventually you get the idea and can just kind of ... close. How many strings are in this language total? Infinite, yeah. So you could describe it as some way of saying the star closure of A union BC. That is way shorter and simpler than trying to list this out, but this has equivalent meaning. All combinations of A and BC any number of times. Questions on that concept? How this relates to something that we've seen before? Right. Also has some similarity to recursion. How?
In order to generate the next string, you have to just reference the same like case of like just adding another one on.
Yeah, imagine a tree where we have the empty string and it's going to have two children, A and BC. Each one of these are going to have two children. Add an A, add a BC. Add an A, add a BC. So we could define any one of these recursively as doing something to the existing string that is its parent. You could then do a depth first search through this. That would kind of be silly. Why would a depth first search be worse than a breadth first search for this?
Because when is there gonna be an end?
Yeah, depth first search is never going to generate BC because this tree goes on forever. So a depth first search is not complete, whereas a breadth first search would be doing this in level order, which would say for any string that is in this language, that process would eventually get there. Whereas with a depth first search, there would be a string that we would never get to, even though we would be infinitely generating strings. We will actually talk about this concept and how to enumerate infinities later on in the course.
Well, a depth first search should work if we use non-determinism, right? Like,
Yeah, if you explore it in parallel,
yeah.
yes. But you would also have to use a frill to a depth first search called a depth limited search and or iterative deepening. That would work. But you would also be generating the same strings multiple times if you did that. But then you get the linear memory of depth first search with the benefit of seeing everything from breadth first search. It's just a little bit slower. So if you run into a memory constraint and it's like, I have to use depth first search or nothing, use iterative deepening. All right, similarity to constructing mathematical expressions. There's an order of operations here. And we'll describe exactly what that order of operations is, but they're given mathematical operations, the union and the concatenation representing plus and times because the order of operations maps. That's the reason we do that. Multiplication comes before addition in an order of operations. Concatenation comes before union. Parentheses come before everything because they override the order of operations. Star closure comes before everything, so we represent it as an exponent because exponentiation happens between parentheses and multiplication. So the order of operations is exactly the same as what you would expect given a mapping onto a mathematical expression. But it uses that same mathematical terminology so that you're already used to that order of operations. It just redefines what each of those symbols mean in terms of some kind of set operation. So primitive regular expressions can be the empty set. This just defines the language with nothing in it. We can also have the empty string, the language of just the empty string. You can use lambda in your regular expressions. You can use the empty set in your regular expressions. Although usually I don't use the empty set too much. Lambda though does show up. We can use any character in the alphabet, the input alphabet. And then we just combine these in some way with the associated operations of star closure, union, and concatenation with parentheses to override that order of operations. And using those tools, we can construct regular expressions for any regular language. if you could draw a DFA that represents a language, there exists a regular expression that maps to that. So you can use set union, concatenation, star closure, and parentheses around any primitive regular expression to create a more complex regular expression, and then you can combine those pieces. So we have the equivalent of primitives, operations, and then you can create objects or complex objects out of those primitives and those operations. Similarly to how you would construct a mathematical expression. So it maps exactly to that idea. So a string that's a regular expression, if and only if it's derived from these primitive regular expressions with a finite number of applications of this. You should be able to kind of, just like you could generate a math expression by saying, here are the numbers, here are the symbols, here are the order you apply the symbols to create the expression. Out of those numbers and operations, you can do exactly the same thing with a regular expression. L of R will just denote the language that maps to that regular expression. So regular expression represents the empty set, the set that contains the empty string. Regular expression denoting the language that contains just the string that is that character. And if R1 and R2 regular expressions, then the language of the union of those languages is just the language of the regular expressions union. Same thing with concatenation. The language of the concatenation of two regular expressions is the same thing as concatenating the two languages together. And parentheses, as you might expect, don't change that meaning. So you can have an arbitrary number of parentheses in a row and it doesn't change the meaning. So you can strip away parentheses if there are multiple sets of parentheses. That's meant to say that you can get rid of extra sets of parentheses without changing its meaning. And yeah, you can same thing, extra sets of parentheses around the language before the star closure, you can strip that away as well. And the entire reason we have these last four rules is that we can simplify regular expressions. And the goal of the first three rules becomes the base case for any recursion. So now you can use recursion to break apart regular expressions into components and recombine them. And oftentimes, as you do that, the individual pieces of that will be smaller than the entire whole considered together. So there's reason to think of them in terms of their components, like that. Let's give you an example. Let's start with giving you a regular expression and asking you to give the language to me in some form of set notation. So to do this, you're going to apply, I'm going to go back to the previous slide here in a moment. You're going to apply these rules until what you have as a result looks like set operations. So your goal is to manipulate parentheses, use those rules to create equivalences, and at the very end of it, you will have a set definition of this language. So go ahead and write down this string, this language definition, L of A star concatenated with A union B. And then we'll go back and take a look at what you can do to it. So using some of these equivalence rules, can you split this apart, recombine it in ways that create a simple set notation defined definition? I'll give people just a little bit of time. This is going to be a bit of a challenge. I haven't really seen this before. So give it your best shot. See if you can find some rules that map to each other. What can you do? And we'll go over it real quick without the expectation that everyone's done this perfect. feel free to talk to people around you as well. This is not necessarily solely individual question, yeah. So I'll get you started with the first step. Maybe that will help get people on the right. So here's what we're starting with. We realize there's concatenation in there, so they could represent the concatenation of two separate languages. So you could split this apart into the concatenation of two languages. Where could you go from there? Yeah,
I was just gonna say, if you're showing it as the definition of two different languages, do not have to put. Yeah,
yeah, kind of like multiplication. If there's no dot there, it just represents that there is concatenation. Yeah.
So our final goal is to have no uppercase L parentheses, right? To strip that out and just have.
Yeah, kind of like a L and L equals, yeah, everything is in set notation. Because we have within this, here we have regular expression language, here we have set language. Here we have regular expression language, here we have set language. So trying to get rid of all of the regular expression terminology and leave it as just the set notation part. It's pretty close. It's in regular expression language, so we define star closure here as fine, but yeah, the plus needs to go away. And you can't make the plus go away in the middle of a large scale language. You want to recombine it after it's split apart. So let's just go over a solution, because I think that's enough ambiguity here that it's good to just see this the first time. So split it apart like we did. Replace the plus with a union, and note that I also put an additional set of parentheses around a few things so that we can split them out from there. And as we add that extra set of parentheses, we can now start to break this apart. And the entire goal of this is to be able to create this associated concatenation where we have the left-hand side that's represented as something that is very simple. So here is the left-hand side. Here is the right-hand side. The language that is just A union the language that is just B is just the set that contains two elements, A and B. And this now allows us to be able to put this together to say, well, if this is just concatenation, then the entire language that's defined here is just something on the left-hand side concatenated with something on the right-hand side. So we can take empty string A, concatenate that together, that's in the language. So A is in the language. Empty string B, A, B, A, B. And we'll see that maybe there is some overlap between that definition. We'll generate the same string multiple times, but that's okay because this is set notation. If we generate a multiple, we ignore it. So we can now combine that and we get a much better sense of what strings are in this language. So this is a general intuitive process that I like to go through when I look at a regular expression or look at a language, to be able to break it down into being able to visualize it in a different way. What are the strings that are contained in this language? Given a language definition, you should be able to go through a process that allows you to list them in some intelligent way. And even for more complex languages like this, if you can break it apart into it's just this language concatenated with this language, now use some combinatorics to throw it together, now we can start to see that there are different ways to look at this. One way would be to just do all the left-hand sides, then left-hand sides with this, left-hand sides with that. It creates kind of an infinity followed by an infinity, which is not great. So you can combine them combinatorically and find some better way to search that space. It's kind of like that difference between a depth first search and a breadth first search. This is kind of the depth first search approach where we're going to explore one side without ever getting to this side because of this ... that goes on to infinity. So if you can find a breadth first way of doing that, combining them such that we ping pong back and forth between these infinities, then we'll have a process that reveals every element of that infinity. We'll talk about that more later, of course, it gets fun. Questions on this process and this result? It's really just for intuition, I find. It is very good for representing it mathematically as well. We talked about the precedents already, just like in math, we need rules to avoid that ambiguity in our expressions. So just like A times B plus C in a regular expression, A concatenated with B union C, there would be ambiguity if we didn't define an order of operations. The given order of operations maps to what you would expect given the math symbol that it uses. So star closure and positive closure come first, followed by concatenation, followed by union, and just like in math, the star for concatenation is sometimes omitted and parentheses override the order of operations that are given. So if you want to do a union before a star closure, you need parentheses. So yeah, R1, R2 is the equivalent of R1 dot R2. You ready for some practice problems of generating regular expressions from language definitions or vice versa? All right. I guess we can first state though in set notation without using the prior rules. Go ahead and see if you can come up with the language for this. So list all of the strings in the language for in some kind of intelligent way. So that's the first practice is here's the regular expression, list the strings in that language in some way that is intelligible. Gesundheit. Again, feel free to work with people around you. It got really quiet in here when I said this is a practice problem.
Yeah.
Everyone's very engaged. I can see it, which is great. But feel free to work with people if that improves your process.
I'm breaking it down, yes, there's the left hand and right hand side, so just always think the bend A or BB. It's kind of similar to that's the problem. And then on the left hand side, yeah, it's A, B, A, B, B, A, B, in the empty string.
Yeah, this is very similar to the last problem. Important to see this concatenation right here, breaking this down into a left-hand side and a right-hand side. That's what that stands for, left-hand side and right-hand side. So the left-hand side just says we're picking one of A or B, but some number of times. So we need to be able to generate that an arbitrary number of times. And then on the right-hand side, for every time we do the next one of these, we need to branch and append it to one of two different things. So you can start to see this algorithmically in addition to mathematically. So my process for generating this is going to be generate the next one of these and then generate all possible concatenations on top of that. So the very first left-hand side is going to be lambda, then A, then B, then AA, then AB, then BA, then BB, etc. The right-hand side is going to concatenate one or the other of these things exclusively. So lambda concatenated with A is just A. Lambda concatenated with BB is just BB. A concatenated with A concatenated with BB. B concatenated with A, B concatenated with BB. AA concatenated with A, AA concatenated with BB. So that's how I'm envisioning the two dimensions of this, where we have a limit on the second dimension, is there are two elements of it. But you can imagine that this also could generate an infinite number, that you kind of have an infinite two-dimensional table. And we'll talk later about how to iterate infinite two-dimensional tables in ways that actually enumerate everything. If that is possible. But now we have an easy way to just read each line, add them to a set, and now we have a process for enumerating these strings that are in this infinite language. Questions on that practice?
What's the set notation?
Yeah, you throw a set around. But if we were gonna do this in set notation, you would just say this is going to be the language that represents the A union B. Star. It's not particularly challenging to produce that necessarily. You do need a second set of parentheses around it now to show that the language definition is that, but yeah. I don't think I ever come back to this type of question in this class, like I convert this into the associated set notation. I just think that if you've seen how do you construct the list of elements in this language from set notation, being able to see that how this converts into that you may have seen before in a discrete course, that's an important part of this. But however your process moves forward, I'm not going to ask you to go through and convert one to the other in the future. I leave that to a math class. That seems like a very math class type of question. In terms of computer science, you might want to write a process that enumerates and outputs as much of this as you can for a while and check something about each one. In which case, this would give you an algorithmic way to do that, which to me is a more interesting computer science question. Yeah, 1 minute left. We can do an English description though. Here's an example of what could you say about this in English? So that's another kind of interesting way to think about a problem is, could you describe in English what this language represents? Not in set notation or in math, but here's a regular expression. Can you find meaning in it? English meaning in it?
Yeah. So it's an even number of A's followed by an odd number of B's.
Beautiful.
Thanks.
That's exactly right. And I don't think there's a shorter, simpler way to say it. So A's have to come together. The smallest even number with a string in front of you is going to be 0. And an odd number of B's, the base case for an odd number is 1. And then you can always add 2 to that, add 2 to that, add 2 to that, but it will always be odd. You can start with 0 A's as the base case and add 2 A's, 2 A's, 2 A's, 2 A's. So yeah, it is an even number of A's followed by an odd number of B's. All right, because we are basically out of time, I don't think we want to dive into the next practice problem quite yet. At the beginning of class, I said we would be done with exam 1 content by the end of the day. I always overestimate how much we can get to because I am as apparently a serial optimist. But no, it's better that we are making sure that we go through this at a reasonable pace that hopefully people are digesting as we do it. So it's probably about one more class worth of material to get through everything that I plan to throw on exam one. But, yeah, question.
When is planning for due?
Week from tomorrow. Week from today will be our review period. You'll have a study guide by tomorrow. Questions? It's getting toward that end of the week. There's serious end of the week vibes in this class today. All right. We'll see you tomorrow. I have office hours in an hour after my next class, if anyone has any questions.